is I want to talk about the method of least squares. I want to talk about the theory behind it and how you would use it in practice. At first, it's going to look extremely limited. It's going to look like it's only going to be applicable in a very small set of circumstances that are not going to be met enough times to merit discussing it for an entire class. It turns out that with the change of variables, this will occur in so many different situations that you can attack a whole variety of problems, that there's a very rich field devoted exclusively to studying this. All right, so here is a brief introduction. Imagine I give you some data point. So this is a test of spring. No, not the nice weather we have outside, the spring from physics, where it's believed that the displacement is proportional to the, the displacement is proportional to the spring constant, I think, as it's moving. I have some stuff like this. What kind of relationship does this look like? Linear. So if you had to deal with any function in mathematics or statistics, you would always choose a straight line. These are the easiest ones to work with. All of calculus is devoted to converting something that's not linear to something that's linear. We're not horrible as a society at looking at data that's roughly linear and getting a good rough sense of what the best line is. Now, best is going to have to be quantified, and there'll be several different ways we can define best fit line. But right now, I think it's all clear. I want a line that goes through this really well. So I need a slope and I need an intercept. Anybody want to guess slope or intercept?
Intercept is 0.
Yeah, let's guess intercept is 0. That seems reasonable. And the slope? 4. Anything else? So if I take 20 and I go all the way up to 20 until 20 hits maybe in through here, and then I go over here. This is extremely accurate, guys. Looks more like 20 is going to 100. So based on the traveling Miller's hand, I would guess a slope of around 5. Also, based on the fact that I wrote these slides, I'm also much more confident that it's probably about 5. Which do you think is the more important number, the intercept or the slope? The slope. Why is the slope more important? Why does the slope matter more?
Because you can predict values like further out.
Well, both of them are needed to predict values.
If you have a point in the slope, then you have the line.
But we need both we need both the intercept and the slope to predict the line. But why is slope more important?
Because slope kind of describes like their direction of the relationship, whereas the intercept kind of grounds that relationship.
You're close.
I was just going to say, it gives you like a better sense of how every point is related to, like how each y is related to x.
So you're all very close. If I want to see what's going to go on around 100, which is going to have a greater effect, the slope or that small little intercept? It's going to be the slope that's going to have the greater impact. So if I have to try to estimate the two, I actually care more about being accurate with the slope than I do with being accurate with the intercept. I mean, again, I'd love to know both of them well, but if I had to pick and choose, I'm more concerned with getting the slope right, because in terms of predicting future relations, that's going to have the greatest change, because I'm going to be increasing x and seeing how y changes. All right, so the data was drawn from xn equals 5 plus 0.2n. So, we were all saying a slope of 5. We should be saying, yeah, okay. So yn was 5xn, and then my xn's were 5 plus 0.2n. So I was marching down the line. And then I chose the error randomly from a normal distribution with mean 0 and standard deviation 4. Errors being normally distributed is not an unreasonable assumption. It's used in a variety of problems for 2 reasons. One, it's actually not a bad fit for reality. A lot of processes tend to be normally distributed. There's a central limit theorem lurking in the background. All the errors somehow combine and become normally distributed. 2, we actually can deal with the normal distribution. And so if we assume the errors are normally distributed, we actually have an extremely well-developed theory. And so the fact that many things are well approximated by normal distribution, and the theory is so nice for normal distribution, makes this a very reasonable assumption. Or maybe popular is better than reasonable. So we get a best fit line of y equals 0.499x plus 0.48. Thus a equals 4.99 and b equals 0.48. So I'm using what's called the method of least squares to get this best fit line. Do we do a good job on both of the parameters? And if not, which ones do we do a good job on? So we get a slope of 4.99. What should the slope be? 5. All right, that's pretty good. We're off by less than 1%. What about the intercept? It should be 0 and we're getting 0.48. That's a sizable error on the intercept. Now again, as x gets very, very large, that extra half is not going to be a significant difference, but it will be a difference. So what I want to talk about now is 3 possible choices for measuring errors. So the more choices we have for how to measure errors, the more options we will have for our analysis. So error measurements. So we have data. It's going to be in a pair form xi, yi, and we believe yi equals axi plus b. So again, right now we're only doing things for a straight line. We do believe that this should hold more generally. So I want some ways to measure error. What's the simplest way you can think of to measure error between prediction and observation? The difference. So error 1, it'll be a function of a and b. It'll be the sum, I goes from 1 to n, of yi minus axi plus b. So observed minus predicted. What's bad about this measurement of error? It can be negative. So if I want to find the best fit line between these 2 points, here's my answer. This will have 0 total error because that error will completely cancel with this error. In fact, I could even do better. I could have a negative total error. All right, so if we just use the difference, that's not going to be a good job. Okay, we could clean this up a little bit. How could we clean it up? Yes?
Take the absolute value.
We could take the absolute values and we could square it. I think I call squaring the second. I equals 1 to n of yi minus axi plus b squared. And then the sum, I goes from 1 to n of yi minus axi plus b absolute value. The advantage of these two is positive errors do not cancel with negative errors. Which one should we use and why? So if you've seen this lecture before, you are not allowed to answer. Oh, that's nice to know that something started. Which method should we use? Or can someone give me an advantage or a disadvantage about either method?
Well, like squares will weigh greater errors.
Yes. So imagine I'm doing some observations. Achoo! Thank you. So that one sneeze really destroyed my analysis. And now if I'm trying to find a best fit line, one bad data point is going to have a pronounced effect on what's going on, far more than it should. There's an entire theory about when you can remove data points. And I'm actually proud that I was removed as a data point in an undergraduate lab. But the problem with this is large errors have huge weights. So it's unequal weighting. And I'll give that a frowny face. Okay. Can anybody think of any issues with this one? Otherwise, it's our winner. Not differentiable. So that's its frowny face, but all errors are equal. So that'll be its positive. And here, differentiable. Okay. The advantage is all errors are equal. So an error of 2 plus an error of 2 is the same as an error of 0 and an error of 4. If I was being paid to do an analysis, I would choose to use this because all the tools of calculus are available. If I was paying for the analysis, I might want this one to be used. Okay, why is this so nice? The reason this is so nice is we have a closed form expression for the best fit parameters a and b using calculus and linear algebra. So again, I'm trying in the last 2 weeks to show you how all the math you've seen up to now connects and can actually be used to do things that matter. So linear algebra is a prereq for this course. It's cutting it close to the wire, I know, but I want to get at least some linear algebra into the semester. Okay? So now I'm just going to back a little bit. All right. So now, our values. So if we use absolute values for the errors instead of the squaring, then we get the best fit value of A is 5.03, and the best fit value of B is less than 10 to the negative 10 in absolute value. So using absolute values, in some sense, does a significantly better job. It's a little higher on the A, but the B is much, much closer. And again, it's those small, every point being weighted equally versus some points being weighted unequally. Okay, and so now I'm going to pause on this stuff for now. Can you raise the screen? Okay, so what I want to do now is I want to talk about how we would use, thank you, how we would use this analysis here to figure out what the best fit formulas are. So we're going to go for a closed form expression. So we want to minimize e of AB. So how would we minimize this function e of AB? What would we use to minimize e of AB? Good. So we want dE dA equals 0, dE dB equals 0. So this is now just going to be a calculus problem. This is a Calc 3 problem. All right, so I want to take the derivative of this with respect to A. So I'm going to get a sum. I goes from 1 to n, and all of this is in the notes which are online. yi minus a xi plus b. The 2 comes down. I now have this to the first power. And now I take the derivative of the inside, which is going to be what? So what will the derivative of the inside be? Yeah. Minus xi. Why is it minus xi? Because we're taking the derivative with respect to a. So a is the variable, not the x. This is one of the things that confuses a lot of people. We're not differentiating with respect to x. Over here, we have 2, sum I goes from 1 to n, yi minus axi plus b. And now when we take the derivative with respect to b, we get minus 1. Well, now we can just do some algebra and regroup. We get rid of the minus and the 2 because it equals 0. And then what we want to do is we want to get a system of equations for a and b and solve. So I can write the first side, bringing everything over as the sum I goes from 1 to n of xi times a plus the sum I goes from 1 to n of 1 times b equals the sum I goes from 1 to n of yi. That's just taking the first equation. It equals 0, so I multiply through by negative 2, and I just regroup things. The second equation over here will become a sum I goes from, oh wait, sorry, this is an xi. So this should be an xi squared here, and this should be an xi. Sorry, because I have to multiply through by the xi. Over here, I'll get a sum I goes from 1 to n of xi times a plus the sum I goes from 1 to n of 1 times b equals the sum I goes from 1 to n of xi yi. And so that is what these two equations become. One of the things you can always do is that you can put in units to check. So maybe x is in meters, a is in 1 over seconds. So what units would y be? If x is meters and a is 1 over seconds, what would y be? Meters per second. And what would b be? Meters per second. I cannot stress enough how important it is to do quick checks like this to see, have you made a mistake? This is how I quickly detected I must have done something wrong here. I've got to have the same units on both sides. This is going to become meters squared per second, meters squared per second. All right, am I doing everything right? No, I'm not. This is the one that has the xi. Okay. So I deliberately did an algebra mistake so I could catch it. Oh, damn it, that was caught on the camera. All right. So when you do something like this, you can quickly catch a lot of algebra mistakes. Now on the next line, I've got meters, 1/seconds, meters per second, meters per second, meters per second. All the units match. Does this mean I haven't made any more algebra mistakes? No, by now you've seen me lecture for a whole semester. Almost, you know I make lots of algebra mistakes. But at least this is now far more likely to be correct. And again, this is the power of putting in units. I once got into trouble for doing this in a math class. You know, math classes, they often don't like you to talk about units. They like you to use words like homogeneity. I don't think this way. This must be all the physics classes I took. I assign units. Things have to have the same units. Whatever the units of y are, that's got to be the same units as ax. That has to be the same units as b. If you do stuff like this, it will really help you keep track of what's going on. We now have a 2x2 matrix. So we get the sum of xi squared. I goes from 1 to n. The sum I goes from 1 to n of xi, the sum I goes from 1 to n of xi, and then the sum I goes from 1 to n of 1, acting on the vector AB equals the vector sum of xi, yi, I goes from 1 to n, the sum I goes from 1 to n of yi. Can we solve this? What do we need to be true to solve? So if I want to solve this system of equations, it's not the case that every system of equation has a solution. If you put in one condition, you will always have a solution. What is that condition? Anything? And what will ensure that this is a bijection?
If AB is in the basis, or in space.
Well, AB is what we're trying to find. Right? We don't know AB. We know everything else. We know the x's, we know the y's. What do we need to make sure that this system of equations is solvable? Something with the determinant. Good. Can anybody bring it home? Yes? Non-zero determinant. If determinant does not equal 0, there exists a unique solution. So if you haven't seen this before, this is really good notation. Backward z exclamation point means there exists a unique solution. Now the question is, does this always have a unique solution? Does it always have non-zero determinant? True if not a moron. So as long as you do not do something of incredible idiocy, it will always have a solution. There's just one thing you have to avoid doing. And we will see in a moment that it is an extremely natural thing to avoid doing. You will not be at all upset about being restricted in this way. Okay? Let's look and try to interpret this. Can anybody interpret what the sum of xi is? Or maybe what a close modification of that might be? Any thoughts? What does it look like?
Well, I mean, the sum of the xi's over n is x bar, so just the sum of the xi's
Yeah.
and x bar.
So this almost looks like the mean. And so in fact, let's put a 1 over n here, a 1 over n here, a 1 over n here, a 1 over n here. And if I do that, I've got to multiply the matrix through by n. Or I can put a 1 over n on the two sides over here. And if I do that, that's now the mean. What does this equal to? So I'm assuming all the points are equally likely to be taken. I'm taking uniform distribution, on x1, x2, xn. 1 over n, the sum I equals 1 to n of xi is the mean. And 1 over n, sum I goes from 1 to n of xi squared. What does that equal? Second moment. So the expected value of x squared. And the sum I goes from 1 to n divided by n of 1, what does that equal? 1. So the determinant of a matrix, if it's 2 by 2, is the product of the main diagonal minus the product of the off diagonal. So the determinant is going to be the expected value of x squared times 1 minus the expected value of x, the mean, squared. This has a name. What is the name? It's the variance. And what do you know about the variance? No. What do you know about the variance?
It's non-zero unless everything is 1.
Oh, okay, but the weakest statement we can say about the variance without knowing anything about the distribution, it's non-negative. So we know the variance is non-negative. All we have to do is remove the fact that it could be equal to 0. And if we can remove the fact that it could equal 0, then we're golden. So only 0 if all entries the same, i.e. all xi identical. What are we trying to do? We are trying to discover how y varies with x. The only dangerous situation is if x doesn't vary. If I'm trying to figure out how y varies with x, and I keep measuring at the same value of x, I do not expect to deduce anything about how y depends on x. This is not an unreasonable restriction to assume. Okay? So as long as we have our x's vary, which we must if we want to see how y varies with x, we're okay. So reasonable. So this is great. So linear algebra comes to the rescue. Linear algebra tells us that the method of least squares will always work. I'm not going to bother writing down what the formula is. The probability of my making an algebra mistake when I invert a 2 by 2 matrix is sadly high. It's in the notes. It's straightforward at this point. And it shows you why some of that stuff from linear algebra, even just at the 2 by 2 level, is important. Now, if instead of trying to think of something of the form just 1 and x, we could actually extend this greatly. When I said it was the method of least squares and I was talking about linear, does it matter that it's linear in xi? Could I have put an xi squared here? Would that have really changed anything? I still would have gotten a linear system of equations in the a's and b's. So it doesn't have to depend linearly on the data. That's one of the powers of it. It only has to depend linearly on the unknown parameters. And that's why this method is so valuable. If it had to be linear in the data, well, all I can do is fit lines. But maybe I think it's a parabola. Maybe I think it's axi squared plus bxi plus c. I could do that. I now have a 3 by 3 matrix. More generally, we could do it as yi minus the sum of, say, ak phi k of xi. K goes from 1 to big K, where phis are now some functions. As long as it's linear in the unknown parameters, we are okay. So all that matters is it must be linear in the unknown parameters. Phis are arbitrary, must be linear in unknown parameters. Okay, so now that we know that, we could go through this. The only thing that would change is now we would have a sum here. We would have not just axi plus b, but we would have a sum of ak phi k of xi. And when we take the derivatives, we would have various phi k of xi's coming out over here. And you would go through, your matrix would be more involved, the coefficients would be more involved. But theoretically, it makes no difference. And for a computer, it makes no difference. Mathematica has built in a function to find the best least squares fit. And you can tell it what functions to use. You want to do best fit quadratic, linear coefficients, figure them out. Mathematica will do that for you automatically, as will all these packages. It's all been programmed. This is why we use E2 and not E1 or E3. In the words of Monty Python, E1 is just right out. Right? Should not even be considered. Okay, bad choice of error. E3 is a legitimate contender. The problem with E3 is that you do not have calculus. You do not have linear algebra. We have a closed form expression here. We can actually write down formulas that you can do this in an advanced class. If anybody's interested, let me know on what the distribution of these unknown parameters, these best fit parameters A will be based on the data. We can do everything we want. It's a beautiful theory because calculus and linear algebra are now available. All right, so I want to do one more aspect of just how powerful this theory is, and then move on to a problem from Cameron's second grade homework assignment, which he and I have bumped up a little bit, so it'll be appropriate to do here. I thought the assignment they gave them was a little bit too easy. So, okay. Anybody know Newton's law of universal gravitation? This is one of the things you need to know to be an educated person, I'm sorry. You've got to know Newton's law of gravity.
It's like gravitational force equals a g amount of q over d squared.
M2 over
D squared.
d squared. Normally we say r squared, just because as Bostonians it's fun to say r. So g is the constant. In fact, it was a huge issue to numerically determine g well. And it was at least, I think, 100 years after Newton before we had a really good value of g. M1 is typically the mass of one of the objects. M2 is the mass of the other. R is the distance between them. The force is pulling you together. What's the most important number in this entire relationship? I'm sorry? Nope. No. Which number? Which number? No, well, R is going to keep changing depending on which points we have. There's only, nope, not many numbers left. The square, that it depends as 1 over r squared. Why is gravity a 1 over r squared force? Actually, it turns out it's due to the geometry of the universe. In a three-dimensional universe, gravity should be a 1 over r squared force. In a one-dimensional universe, it would be a 1 over r. In a four-dimensional, it would be a 1 over r cubed. There are very natural reasons. I heard a great argument in a book by Feynman. So imagine you have a point source at the center of a sphere. And we'll assume that gravitational pull is coming from yankage. And so the area of a sphere of radius r is 4 pi r squared. And so if I take a small disk, the further out the disk is, the less of a pull it's going to feel if I assume the pull is distributed equally across the surface of the sphere. So if I want the total pull to be constant, no matter how far out my sphere is, the force has to be dropping off like 1 over r squared to compensate for the fact that the surface area is growing like r squared. This is not a proof. We've talked about whether or not there is a God and the consequences this has. You can set up the laws of the universe any way you want, or other people can. This is just a heuristic that maybe an r squared is a reasonable thing to expect if I want things to be constant. Well, the problem is, let's say we don't know it's r squared, and we're trying to figure out what that number is. This is not set up for the method of least squares because it's now depending non-linearly on the unknown parameter. What can we do? Take logs. So the other one I will do is I'll go back a little bit before Newton. Kepler had 3 laws of planetary motion. Okay, one was that planets travel in elliptical orbits about the sun. Another is they sweep out equal area in equal time. And another one is that, I always get this wrong, the period squared is proportional to the semi-radius, the length of the semi-major axis cubed, or maybe the other way around. This is the least obvious one. And these were the 3 laws that helped Newton figure out what the law of gravity should be. What force would give you this motion? And so if you want to try to figure out, if you think that the period to some power P1 is proportional to the semi-major radius to another power P2, you want to figure out what P1 and P2 are from the data. This is highly nonlinear. Well, Kepler ends up having squares and cubes. Things are nice. But I can, of course, divide both sides by P1. Or I can just say, I can always change my units and take P1 to the first power. And you get T is K to the 1 over P1, R to the P2 over P1. And now I've just got T to the first power. And so in some sense, this is a good thing to do because I only care about the ratio of P1 to P2. I don't care about their actual values. That just changes the numerics of what K is by how I'm writing it. Because it turns out to be a ratio of 1.5, I can write it very nicely. So I'll write it as T is some constant kappa times R to the A. And now if we take logs, the log of T is going to be A log R plus the log of kappa is going to be A log R plus B. So we can take a highly nonlinear relationship and reduce it to a linear relationship. And now we can use the method of least squares to find the best fit values for A and B. And so now yi becomes the log of t, and xi becomes the log of r. So as an optional homework problem, I give you the values. I can't remember if I include Pluto or not. I think when I originally started doing this problem, Pluto was still considered a planet. By the time I came to Williams, Pluto was no longer a planet. I can't remember if I included that. But if you actually put the values for the planets, you get incredible agreement. So what I like about this problem is we've reviewed Calc 3, we've reviewed linear algebra, we've seen basic probability come into play, we've seen how our previous classes come into play, we've seen the log trick come into play to just show us how we can simplify things. And this is one of the most powerful applications in probability and statistics. This leads to regression, this leads to gathering good data and dealing with it. Okay, any questions on this? Yes?
I think you dropped the square on,
Oh, almost surely. What did I drop the square on?
the second error, or the least square.
Oh, yes, thank you. When I erased too much. Yes, thank you. Okay, all right. Any questions on, any other questions? All right, so I'm going to tell you the original game that Cameron had for second grade, and I'll tell you the modification. So in the original version of the game, you roll 5 die one at a time, and as you roll, you have to decide, do I want to use this for how many dollar bills I have, how many quarters I have, how many dimes I have, how many nickels I have, how many pennies I have. And once you fill up a spot, you can't fill it up again. And so to save time, we decide to roll all 5 die at once, and you get to choose which you put where. So even second graders know immediately whichever number you roll as the highest, that's your dollars. Whichever number is your lowest, that's your 1. So a natural question to ask is, what's the expected value? What do you expect to roll for something like this? So I wrote a computer program. It's about $7.05. It's a really good theoretical problem. Can you theoretically compute what this is? It was easy to do 1 million or 10 million games and get a really good estimate. Let's look at a simpler problem just because we've got about 15 minutes left. With 15 minutes left, what I want to do is I want to look at, let me erase this. I'm going to roll n die. Each is k-sided, so equally likely to get a 1, a 2, or all the way up to k. And whatever the maximum is, so you earn $1 minus the maximum roll over k. It's reasonable to divide the maximum roll by k. Do you want to play this game? No cover charge. Do you want to play this game with me?
Yeah.
Yes. Why?
It's free money.
It's free money. Worst case scenario, if the maximum roll happens to equal k, you get nothing. If the maximum roll is less than k, you earn money. The question is, how much money do you expect to earn? And no, I'm not playing with Cameron, giving him a deal like this. Okay? So what do you think? So what is the probability the maximum is m? So we can actually write this down in closed form solution. This leads to a subject called order statistics. I can't remember right now if order statistics is an appendix in the book. It might have just been completely killed. But there's a great idea in terms of how you would calculate this. So the probability the max equals m is the probability the max is less than or equal to m minus the probability the max is less than or equal to m minus 1. This is a great way to analyze a lot of problems. If I want to figure out what is the probability that exactly something happens, calculate the probability that you get that or less, and then subtract the probability you get less. Well, since things are discrete, if it's less, it's got to be at most m minus 1. This is a wonderful, wonderful technique or trick to calculate probabilities. These turn out to be significantly easier to calculate. I would much rather do 2 simple problems and combine them than 1 hard problem. To calculate the problem that the maximum is exactly m, oh dear Lord, I have n rows, at least one of them must be a m, nothing can be higher, and others can be lower. So for instance, if you're rolling 5 die and you want to calculate the probability that the maximum is a 6, there are 31 different configurations that lead to a maximum of 6. What's the probability that the maximum is at most m? What would that be? Any thoughts? I roll n die. Each die has k sides. All k numbers are equally likely, and no number can be larger than m. So if I had 1 die, what's the probability that on that 1 die I don't get anything larger than m? What would it be? 1 die, nothing larger than m. So if we had a die with 6 sides, a normal die, what would be the probability I don't roll anything larger than a 5? 5/6. So in general, it's m over k to the mth power. I'm sorry, to the nth power, because we have n die, minus m minus 1 over k to the nth power. So we have a really nice formula for the probability. So if I want to find the expected value, it's going to be a sum. M goes from 1 to k of m times m over k to the n minus m minus 1 over k to the n, like this. Now what I want to do is, we've got 10 minutes. I want to go through and do the algebra as to how you would attack this. I want to come up with a theoretical prediction, and I want to test this against the method of least squares. So I'm going to show you some tricks as to how you would handle sums like this. All right, so I have a sum. M goes from 1 to k of m over k to the n, minus a sum. M goes from 1 to k of m minus 1 over k to the n. I don't want an m here. What would I want here instead? If you look at this, what would be a nicer thing algebraically to have here?
K.
Not a k. See, here I have m over k to the n. I'd rather have an m minus 1, because then this is essentially just a shifted index version of this. Maybe the n's differ. So what I'm going to do is I'm going to write m as m minus 1 plus 1. And now I get a sum. M goes from 1 to k of m over k to the n, minus a sum. M goes from 1 to k of m minus 1 over k to the n. And now I have minus a sum. M goes from 1 to k of m minus 1 over k to the n. So if I look at this, when m equals 1, I get 0. And for all the other values of m, it's canceling what I have here. It's just shifted over by 1. the only term that survives is when k equals m. So we're left with, I'm sorry, when m equals k, so we're left with k over k to the n, minus, this is all canceled away, and now we have a sum, we have a 1 over k to the n, a sum, m goes from 1 to k of m minus 1 to the n. Okay, so now we just have to keep doing some algebra. And so I can approximate that sum by an integral. And so the sum, m goes from 1 to k of m minus 1 to the n, is approximately the integral. I go all the way up to k minus 1 of x to the n dx. This should be x to the n plus 1 over n plus 1, a value of 1 and k minus 1. The 1 doesn't matter. It's approximately k minus 1 to the n plus 1 over n plus 1. And so now we get k minus, and watch and see if I make any mistakes, 1 over k to the n, k minus 1 to the n plus 1 over n plus 1. All right, well, if I look at what's going on here, okay, so I have a k minus 1 over k to the n, so that's 1 minus 1 over k to the n. I have an extra k minus 1 over n plus 1. The 1 over n plus 1 is going to be much, much lower, and I'm going to be left with the main term will be k 1 minus 1 over k to the n, plus now something of size minus small. But this was doing the expected value of m. I'm not supposed to do m. I'm supposed to do m divided by k, right? So I have to put in a 1 over k. And that's why I'm not really worrying about the small. When I put in the 1 over k, that k now drops away. And now this is damn small. Okay, it's even smaller. And I was doing 1 minus, right? So I earn 1 minus this, 1 minus above, which should be approximately, the 1's cancel, and I get 1 minus 1 over k to the n. This is about 1 minus 1 over k to the k times n over k. What is 1 minus 1 over k? Approximate to the kth power, this is approximately. One minus 1 over k to the k. This is about what? You need to know this limit. This is the limit for e to the negative 1. So e to the x is 1 plus x over n to the n as n goes to infinity. So here I've got negative 1. So this is approximately e to the negative n over k. Oops, and I dropped the n plus 1 over here. Sorry. So I should have a 1 over n plus 1. I should have divided by n plus 1, divided by n plus 1. So here's my theoretical prediction. It should be about e to the negative n over k divided by n plus 1. So if I take n to be large, say 100, and I increase k, I would expect this kind of relationship. Is this linear with k? No. But if I take a logarithm, it's now linear with 1 over k. All right, so I'll plot it against log of 1 over, I'll plot it against 1 over k, not k. So which one is that? Okay. So, oh, I forgot to turn it on. All right. So we should make it. So I'll skip the stuff for now. Okay. So here is the problem we were talking about. We're tossing a die, k sides, all equally likely, take the largest number. And here's the theoretical prediction, e to the negative n over k over n plus 1. Did all of those heuristical reasonings look fine to you? That this is what the answer should be? This is the advantage. This is why I want you guys to learn how to program. This is why I'm so insistent on this. And if you think it was bad this year, it's going to be a little bit stronger next year. For theoretical calculations, if you can get some data, you can see how reasonable your approximations are. There were some approximations we made. How good were they? How dangerous are they? So here is a semi-log plot. So again, there's a bit of an art in knowing how you want to present the data. I'm taking the logarithm of the outcome, but not the logarithm of the underlying variable. I like the 1 over k. I'm plotting things against 1 over k, not against k. Because if you look at the exponent, when I take the logarithm, I expect it to be linear in 1 over k. Does this look like a straight line? It's not horrible. So now I go to Mathematica and I use their fitted model, and I did it against the original data, the log-log plot, and then the semi-log plot. The semi-log plot is the last one. And the fitted model gives negative 4.61468 minus 54.2127x. So the answer, we said, should have been the following. I chose n to be 100, and so that should give exponent negative 100 over k divided by 101. When we do a semi-log, we get the following. So it should be, my coefficient should be negative 100. I've got negative 54. And I should get negative log of 100. Negative log of 100 is negative 4.605. Not bad. Sadly, it's the one I care least about. Right? I told you at the beginning of the day, the one I care most about is the slope, and the one I got right was the intercept. That's not bad. I'm getting the intercept essentially to 2-3 digits. It's about 2 digits. It's about 2 decimal digits. Why am I so off with theory? I'm off by about a factor of 2. Now, how many of you have ever done a physics lab or a chemistry lab or a bio lab? All right, the camera can't see you. How many of you have written up your lab before you went in? Oh, very honest class. All right. So a lot of people write up labs before they actually do it. Sometimes instructors deliberately miscalibrate the instruments so that if your data actually fits properly, you know something is wrong. Frequently, in combinatorics and probability, if you're off by a nice factor, you can often figure out where the mistake is. What do you think that negative 54 is supposed to be? It's probably not 100. It's probably not negative 100. I'm way off for negative 100. What do you think that negative 54 is probably? If you had to guess. What do you think? Negative 50. And so if we try negative 50, it means I'm off somehow by a factor of 2. Is there a way for me to figure out where that factor of 2 is coming from? And the answer is yes. The place where that factor of 2 is coming from our approximation of the sums of integers. So unfortunately, it's now been covered up. Oh well. But we were estimating the sum of m minus 1 to the n, m goes from 1 to the k, as approximately k minus 1 to the n plus 1 over n plus 1. It turns out a better estimate is k minus 1 plus a half to the n plus 1 over n plus 1. And I'll send some notes about this, that I didn't keep enough terms in my approximation. Normally, come on, k is huge, minus 1, a half, does it really matter? Well, the difference with that extra a half is now we get k minus 1 half to the n plus 1 over k to the n. Yes?
Why?
I'm sorry?
Why are you adding in the half?
This is a better estimate for this sum than this. The integral test was too crude. I'll send notes on that for additional comments. But the error in the integral test was large enough to make a mistake here. When you use a more refined of 1/2 here, what I now get is I get a k coming out, and I get a k 1 minus 1 over 2k to the n. And now if I put in my k over k, I now get k 1 minus, I'll write it as 1/2 over k to the n over k, and there is e to the negative n over 2k. And instead of 100, I should have 50. So I made that mistake. I did not see that when I was doing the initial experiments. By breaking things up and doing the statistical analysis, that led me to discover this. All right, so for the last few seconds, I want to just show some other data very briefly. This is power laws. So this is looking at the 25 most populous cities. Just trying to get the thing back in focus a little bit. Feel like a drunk. All right. So Looking at the 25 most populous cities, if you do a plot, here is the plot. It does not look linear, but if we do a semi-log plot, if we do a log-log plot, that looks pretty linear. And again, this is something I want you to get out of today's lecture. If you do log plots, semi-log plots, if you play with the data, you often get linear relationships. This is population. If you look at plots with log-log, again, beautiful straight line. This is looking at word counts, the rank of the word and how often that word is occurring. Incredible how well this is described by a linear relationship. And what's great is it doesn't matter what the exponent is. The method will pick this all up. All right, so I will send you some possible topics for the last 2 days of class.